Hello, my name is Randall Pike. I'm teaching the D200 section of Math 232. Along with my colleague Brenda Davison, who's teaching the D100 section, we'll be preparing these lectures that will cover this course, taking turns presenting specific sections. Today I'll talk about section 1.4. So let me share that with you here. Just give me a second. Okay. All right, so I believe this is being shared properly. Yes, it is. Good. Okay, so today we're going to talk about vectors in Rn. First of all, so we're going to generalize the notion of vectors that we've learned in R2 and R3 into what we say higher dimensions, n being the dimension. And then we'll talk about the very important concept of a subspace. Okay, and then this concept of subspace will rely on these two notions of closedness. They are, and they're referring to the two algebraic operations that we've defined on vectors, namely vector addition and scalar multiplication. So let's start with the notion of Rn. What do we mean by vectors in Rn? Well, these are vectors that have n components. So let's take one of these vectors in Rn. I'll write it out component-wise, v1, v2, all the way to vn. And let's take another vector, w, let's call it, in Rn. So it has n components, and I'll write them down as w1, w2, down to wn. So there's two vectors in Rn, Now, the notion of equality is exactly as we've seen for R2 and R3. We say that v is equal to w as a vector, as vectors, if and only if all these components are the same. So v1 is w1, v2 is w2, etc., all the way up to the last component, vn and wn. Okay, so we recognize equality between vectors when we see that they have the same components. We have the notion of vector addition. Now, when we're in dimensions greater than 3, so n is greater than 3, we can no longer make a sketch of the geometric interpretation of vector addition and scalar multiplication, so we'll just rely on the algebraic definition of vector addition and scalar multiplication. So vector addition is defined the following way. So I'll take two vectors in Rn. Let's take this v and w. So I'm going to define this vector v plus w, and to define a vector, we specify its components. So the first component will be v1 plus w1, that is the sum of the first components of the v and w, and the second component would be v2 plus w2, and all the way down to the last component, vn plus wn. So that's the nth component of this vector, vn plus wn. So I've defined another vector in Rn from the sum of these two vectors, v and w. And similarly, for scalar multiplication, we'll take scalar k, and multiply it by v. And I'll just mention up here that scalars, when we see the word scalar in linear algebra, we mean real numbers. Okay, so real numbers. There's many kinds of numbers, but we'll be working with real numbers when we talk about scalars. So I'll take a real number k, and I place it in front of the vector v. It denotes a new vector called kv, and this new vector will be defined by its components again. So k, the first component will be k times v1, the second component k times v2, and down to k times vn. So I've defined another vector in Rn, beginning with a vector v and a scalar k. So the same, exact same definitions as we saw in R2 and R3. Okay, now we should insert here, I think, also the important notions of linear combinations. So linear combinations, that will come up later. It's the same notion as we've seen in R2 and R3, linear combinations. So a linear combination, let's write it this way. Linear combination of, let's take k vectors in Rn. Okay, so there's k vectors in Rn is a sum of the form. So I'm going to use both vector addition and scalar multiplication. So it's a sum of the form C1 V1 plus C2 V2 all the way up to the kth one, okay, where the Ci's are scalars. So these are real numbers. So that's a linear combination of k vectors in Rn. Okay, k can be any number here, any integer. And then the other important notion that's related to linear combination is the span of a set of vectors. So that was denoted by the word span. So span of this set of vectors, v1 to vk. In set notation, it's the set of all linear combinations. So let me write C again here. So C1 V1 plus all the way up to k, ck vk, where Ci's are real numbers. So I'm looking at all possible linear combinations. That's the span of the set of k vectors. Okay, so the same notion as we've seen before. Okay, so let's continue on. Now we're moving on to an important concept of closure, which will lead us to the definition of a subspace. So there's closure is in reference to the two algebraic operations that we have on vectors, the addition and the scalar multiplication. So there's a notion of closure referring to the addition of vectors, and there's a notion of closure referring to the scalar multiplication. Let's look at these separately. So we define a subset of vectors. So S is a subset. Notice the term subset here. So I'll emphasize that later on in this lecture also. So we're talking about certain subsets of vectors. Okay, a subset of vectors is just a collection of vectors, any number of vectors in it. We'll specify that it's not empty, so there's at least one vector in there. So a non-empty subset of vectors in Rn, we say is closed under addition if, whenever you take two vectors in the set S, and you look at the sum of those two vectors, it is also in the set S. So that's the notion of closure. If you're inside this set, that is, if you take two vectors inside the set and you add them, you will remain in that set. That is, their sum will also be a vector in that set. Okay, so that's where the word closed comes into play here. So let's look at some examples. So here's a set S1, and it consists of just two vectors. So they're explicitly written out, 1, 0, 0, and 0, 1, 0, two vectors in R3. Is it closed under addition? Well, we have to check whether, if I take two vectors from that set and I add them, is that vector, the sum of them, in that set? Well, here's the two vectors. Let's call it u and v, u and v. So I want to check whether u plus v is in S1. Is it in S1? Well, let's look at the components of u plus v. So I'm going to use the, notice there's two ways to write components, vectors in component form. This way as a row vector, and above there I was writing them as column vectors, which is what you see in the textbook. But both of them are equal for us. We can write them in either way, and it depends on which is more convenient. Here it's going to be more convenient for me to write it in this row vector form. So I'm going to do that. I'm going to add u plus v and look at their components and check whether that new vector is in the set here. Okay, so u plus v component wise is going to be 1, 1, 0. Okay, so that's what that vector is in R3, and we see that it is not in S1. Okay, and so we say that S1 is not closed under addition. Okay. Notice that in the definition, the key word here is for all. All right. So it may in fact be true that for certain selections of U and V, if you add them, they may still be an S, but that doesn't in itself mean that the set is closed. It has to be true for every possible choice. In this particular case, there's only two vectors, so there's only one choice of two vectors from that set. So we've shown that it doesn't work for that one, and it only has to fail for one example for it not to be closed. Okay, so the proving that a set is closed, as we'll see in the next example, where we have an infinite set of vectors, um, in principle requires you to check every possible selection of two vectors and adding them. Okay, so it's an exhaustive search. Here, if you find one example where the sum is not in that set, then you're finished. You've proven that it's not closed. However, to prove that it's closed, you have to check every possible selection of two vectors and add them. So let's go on to the next set, which is fundamentally different, this set S2, than the first set S1, in that there's infinitely many vectors. But these vectors all have a special form. They have three components, so they're in R3, but the first two components, notice, are integers. Okay, so all vectors that have integers in the first two components. Is this closed under addition? Well, let's take any two vectors in there, and let's see what we get when we add them. So let's take a U to be A1, B1, 0, and a V to be, let's call it A2, B2, 0. Okay, so there's two vectors from the set S2 because they have the form specified in the definition of the set S2, namely that their first two components are integers. So A1 and B1, A2 and B2, they're all integers. So let me write that down. A1, B1, A2, B2, they're integers. Okay, so I have selected two vectors from that set. Now notice I'm starting off this proof with the ambition to show that it is closed because I'm not specifying any particular two vectors. Okay, so U and V are any two vectors because I haven't specified what the A1, B1, A2, B2 are. And this is the approach you have to take if your goal is to show that it is closed. Okay, because you have to show that it's closed under addition for any two choices of vectors. So I've made my arbitrary choice of two vectors. Now let's add them up. So U plus V. Now I want to check whether this vector U plus V is going to be in the set S2, which means I have to check whether its form is as specified in the definition for S2, namely that its first two components are integers and the third component is 0. Is that the case here? Well, let's write out what the components of U plus V are. So once again, this is just adding the two components here. So A1 plus A2 is the first component, B1 plus B2 is the second component, and I have 0 for the third component. So I've added these two vectors, these two arbitrarily chosen vectors from S2. They have this form: first component A1 plus A2, second component B1 plus B2, third component 0. Now I'm going to rewrite that as A tilde, B tilde, 0, where now I see that A and B tilde are integers because when you add two integers, you get another integer. So in other words, A tilde is this integer A1 plus A2. I haven't specified what A1 and A2 is. All I know is that they're integers, but I do know that whatever integers they are, their sum is an integer, which I'm calling A tilde. Similarly for B, the second component, B1 plus B2 is also an integer, which I'll call B tilde. So I've proven that the vector U plus V has the form specified in the definition for S2. So S2 is closed under addition. Under addition. Okay. So you see how these two proofs differ. In the case S1, we proved the set is not closed by showing just one example where two vectors under addition do not does not lie in the set. Whereas in the second case, where the set is closed, it's more work. In other words, you have to select any possible pairs of vectors and show that when you add them, you still remain in that set. So I had to do it abstractly, and you'll be obliged to do it abstractly when you're trying to justify that a set of vectors is closed. Okay, so S1 and S2. Let's move on to the other notion of closure, which is related to the second algebraic operation we have on vectors, that is scalar multiplication. So we say that a set, non-empty set of vectors, subset of vectors in Rn, closed under scalar multiplication if you pick any vector in S and any scalar in R, this new vector is also in S. So you see the notion of the word closed appears here again because you take a vector in the set and any scalar, and the new vector you get, C times U, is still within that set. So you haven't left that set. The set is closed. You cannot get out through scalar multiplication in an informal way. Okay, so let's go to S2. So S2 is that set that's defined just above us there. Is it closed under scalar multiplication? Okay, now this one, we're going to use the fact that, I'm going to highlight it here, that our scalars are real numbers. Okay, whereas in this definition, these components, although they're real numbers, they're very special types of real numbers. They're integers. Okay, so will that form of S2 be maintained, for a vector in S2, be maintained under scalar multiplication? It may or may not. So for example, let's look at an example. Let's take 3 times this vector u up there. Okay, so what is 3 times u? So it's going to be 3a1, 3b1, and 0, okay, for that vector u above there. And this is in S2. Okay, so that vector multiplied by that scalar 3 is also in the set S2. Okay, but that's not enough to prove that it's closed. Remember, you have to prove that it's going to be closed under any choice of scalar and any choice of vector u. Here my vector u is arbitrary. Okay, so you can think of it as being any of the vectors in S2, but my scalar wasn't arbitrary, and that's the key here. So I'm going to pick another scalar, pi. How about that? So pi times u is going to be pi times a1, pi times b2, and 0. Okay, now if a1 is not 0, then pi a1 is not an integer. And similarly for b2. So if b2 is not 0, then pi times b2 is not an integer. Therefore, pi times u is not in S2 if a1 and b1 are not 0. Okay, if they're both, or b1 I should say, okay, just one of them has to be non-zero. Okay, because then one of these components will not be an integer. Okay, so that's, I'm using the fact that pi multiplied by any integer is not an integer. Okay, I'm using that fact. Okay, now S3, notice the difference with S3 now. It looks like S2, doesn't it? It's vectors in R3 with 2 components being arbitrary numbers, in this case real numbers, and the third component being 0. This one is closed under scalar multiplication. Yes, it is. Okay, so let's prove that one. So let's take C, now any real number, times this vector u, and I'll get CA1. Sorry, I should write that down as x here. Okay, so let me take another vector. I shouldn't use the same symbols here. Okay, so my vector is going to be u x y 0, where x y now are real numbers, okay, not integers necessarily. And let's take a real number c, multiply it by u. I'll get cx cy 0. Okay, so now c's an arbitrary scalar. So I've taken an arbitrary vector u in S3. I've taken an arbitrary scalar c. And now I have to check, is this vector, this new one here, of the form specified in the definition of S3? So I'm going to rewrite that as an x tilde and a y tilde and a 0. And because c times x is a real number and c times y is a real number, I know that these two numbers, x tilde, y tilde, are real numbers. And so c times u is in S3. Okay, now I've proven that the set S3 is closed under scalar multiplication because I've proven it for every selection of vectors in S3 and every selection of scalars C. Therefore, we conclude that S3 is closed under scalar multiplication. And you can check too that it's also closed under addition. Okay, that's a good proof for you to do under addition. So that's an example of a set of vectors that is closed under both of these operations, these both algebraic operation. Okay. Okay, so let's move on to a very important notion in linear algebra, that of subspaces. Okay, so subspaces is going to use this notion of closure. Okay, so to begin with, a subspace is a subset. Okay, so a subspace of Rn is a non-entity subset of Rn, so it's a collection of vectors, but it's a special kind of subset. It has these properties. It's closed under addition and under scalar multiplication. Okay, so it's a subset of vectors that is closed in those two senses, both of them. So I'll just go back up to here, and let me just write it in here that this S3 is a subspace. Okay, once you've proven it's closed under addition, which you can do yourself. So S3 is a subspace. And we can see from the dimension it's in R3, so S3 is a subspace in R3. Let's look at some other examples. So now this set W here is defined. So this is a subset of vectors in R2, and we're asking whether it's a subspace. So now we have to check both those closure properties. And now look carefully at the definition of this subset. So it's vectors in R2 where the first and second component are positive numbers, positive real numbers. Okay, so that's a set of vectors, and you can sketch it out. It looks like this, right? So it's this quadrant up here, except for the edges. Okay, so x and y being positive. So all those vectors are this set W. Is it a subspace? Well, let's check for closure. Addition. So let's take two vectors here. So let's take u equals x1, y1, w equals x2, y2, where these are both xi and yi are both positive. Then u plus w has components x1 plus x2 and y1 plus y2. And we see that because x1 and x2 are both positive, this sum is positive, and the y1 plus y2 is also positive. So closed under, so this is in the set. Okay, let's write that down here. So u plus w is in the set. Okay, so it is closed under addition, but what about scalar multiplication? Okay, so what I've just proven on for the addition part is exhaustive proof. I've taken arbitrary two vectors in W and I've added them and I've shown that their sum is in W. So I've proven that it's closed under addition. When I go to scalar multiplication, if I want to show that it's closed under scalar multiplication, I'll need to select any vector and any scalar. Okay, so it would have to be an exhaustive proof if it turns out to be closed under scalar multiplication. However, if it's not closed under scalar multiplication, then you just have to exhibit one example where the scalar product k times v for v in W is not in W. So I'm going to use my intuition and see that something's going to go wrong here when you multiply a vector by a negative number. So let's take minus 2 times this vector u. Okay, so I've taken an arbitrary vector u, and I've taken a specific scalar minus 2. Okay, what are its components? Well, it's going to be minus 2x1, minus 2y1. All right, but now, because x1 and x1 and y1 are positive, we have 2x1, minus 2x1 being negative, and minus 2y1 being negative. Either one of these shows that minus 2u is not in W. Okay, so not closed under scalar multiplication. Okay. So in some sense, proving a set is not closed is easier in that you just have to find one example, whereas proving that it is closed is more work because it has to be an exhaustive proof. So this one is not closed under scalar multiplication because I found one example. Actually, I found many examples because I chose any vector u there. I chose a specific scalar. And you can see the way this is going to work. As long as your scalar is negative, then multiplying one of these vectors by that scalar will result in a vector that's not in the set. Okay, so it's not closed. All right, so line passing through the origin in Rn. Okay, so remember, these are lines of the form. So here's a vector on the line, point on the line. It's just a scalar multiple of a vector d. Okay, so is this one a subspace? Well, let's check for closure. So I'll take two vectors. So let's take x1 vector to be t1 times this d, and x2 vector to be t2 times d. So I've selected 2 points, 2 vectors from this set. Okay, so they are defined by these scalars t1 and t2. And then I look at the sum, x1 plus x2 vector is going to be t1d plus t2d, which I can rewrite using distribution, t1 plus t2 times d, which I'll just write as another scalar t times d, is in the set. Okay, so when I add two vectors from that set, which is aligned to the origin, I get another vector which is in that set, namely it's on the line to the origin. It's a multiple of d. So it's closed under scalar multiplication or vector addition, and then scalar multiplication will take c times x1 will be c times t times d, and I'll just group using the distribution again, c times t times multiplying d, and I'll call that t hat times d is on the line. Okay, so it is a subspace. So this one is a subspace. Subspace. Okay, I've proven that it's closed under vector addition and scalar multiplication. Now the other case here, a line passing through the point and parallel to this vector. So this is a different situation in that the set it's a line, but it's not passing through the origin. Okay, so what happens in this case? So let's take 2 points here and see whether they're going to be in the set, in the space on the line or not. So let's take a W to be, so this, let's call this one here okay, W equals, so 1, 0, 0 plus T1 times 0, 1, 1. Okay, that's my W. And my other vector, so let's do scalar multiplication. So W is this, and therefore C times W is going to be C times 1, 0, 0 plus C times T1, 0, 1, 1, which we see as C, CT1, CT1. Okay, so I've taken a vector, an arbitrary vector, I've multiplied it by a scalar C. I end up with this vector, and our question is this a vector? Our question is it on this line? So in other words, can I write this as 1, 0, 0 plus something times 0, 1, 1? That's the question. So if it was, then it would be on that set, in that set, but it's not going to be. The only way it's going to work is if C is 1. Okay, if C is not 1, then this vector C, CT1, CT1, this vector here, is not of this form here unless C is 1. Okay, so it's not closed. Not closed under scalar multiplication, so it's not a subspace. Okay, not a subspace. Okay, so only when C is 1, but then that's just the same vector W. Okay, now a plane passing through the origin, is it a subspace in Rn? So remember how we defined a plane in Rn. So let me get that color. So X, it's a set of all points that are scalar linear combinations of these two vectors. Okay, so V1 and V2. Okay, so and V1 and V2 are linearly independent. Linearly independent. Independent. So if I take two vectors there and I add them, do I get another vector that's in that set? Okay, so let's take a let's take it a vector U to be T1 V1, and let's take a vector V to be S1 V1 plus S2 V2. Okay, so I've taken two vectors U and V in that plane. I'm going to add them up. U plus V is going to be, so I can group together these scalars T1 plus S1 multiplying V1 and T2, yes, T2 plus S2 acting on V2, which I'll write as a tilde T1 V1 plus a tilde T2 V2, and I see that it is in the plane. Okay, so it is a combination of v1 and v2. So I took two arbitrary vectors in the plane, I added them together, and I got another vector in the plane. So it is closed under vector addition. And let's check scalar multiplication. So I'll take a scalar c, I'll take this vector u. What are its components? Well, it's going to be c times t1 times v1 plus c times t2 acting on v2, which again, I see that to be a certain scalar multiplying v1 plus a certain scalar, which I'll call t2 hat, multiplying by v2. So it is in the plane. And therefore, it is a subspace. So it is a subspace. All right. So proving that a subset of vectors is a subspace, you have to prove that it's closed under both vector addition and scalar multiplication, which means you have to do some kind of abstract proof, because you have to pick arbitrary vectors and show that the closure of addition and scalar multiplication holds arbitrary vectors and arbitrary scalars. And that's what I did here. So I didn't pick any specific ones. And actually in this problem, I couldn't pick any specific ones because the plane itself is not defined explicitly. But the proof would still have to be abstract, even if it was defined explicitly. All right, another question here, another subset of vectors. This one is a very simple subset of vectors. It's the zero vector. But the set is consisting of only just that one single vector, the zero vector. Is this a subspace? Well, this is easy because you only have one vector in there, so you can only choose that vector for your scalar vector addition and scalar multiplication. And therefore, it is, because if I take the two vectors in the set, which I have no choice but to pick 0, I get 0. Right? And if I take any scalar and multiply it by the 0 vector, we get the 0 vector. Okay, so it's closed under addition and scalar multiplication. Notice this will not be true if the vector was not the 0 vector. So that's an interesting example for us. It's the only subset of vectors consisting of one vector that is a subspace. It has to be the 0 vector in that set. Another interesting case, a simple case, is the subset containing all vectors in the space Rn. And this is yes again, because when I add two vectors in Rn, like I defined at the beginning of this page, it is in Rn. Okay, I do get a vector with n components. And if I take any scalar and multiply it against any vector in Rn, the answer is also in Rn, the way I define scalar multiplication. Okay, so there's two subsets of vectors, which are in some sense simple ones. They're either the single 0 vector, or they're all the vectors in Rn. These are two examples of subspaces. And because they're kind of simple, we call them trivial subspaces. Okay, so we're usually interested in subspaces that are not trivial subspaces. Okay, so these are going to lead us to this picture here. What are the subspaces? I'm going to draw it above here. What are the subspaces in R2 and R3? Well, in R2, I can make a pretty good sketch. Okay, so we have, as we've just seen, we have the 0 vector. There it is. Okay, and then we have, I'm going to follow the notation in this definition here. So in R2, there's the trivial subspace I just denoted, the blue dot. Lines through the origin. So remember the proof above about the line through the origin being subspace. So there's my line through the origin. Okay, that's a subspace. And then I have the other trivial subspace, which is just all the vectors. Okay, so there's a sketch of all subspaces of R2. There's not 3 examples here. There's infinitely many because this line in the middle, this one here, there's many choices of these lines. Okay, so any line going through the origin could have been one of these examples. So there's infinitely many examples here. So there's my R2. Now for R3, 3 dimensions, a little bit harder to sketch, but still we have the trivial subspace and all of R3. So there's the 2 trivial subspaces, the 0 vector. Yeah, so the 0 vector and R3 are there. But now in R3, we also have this notion of lines again. So lines in any dimension will be a subspace. But the planes also, we've seen above, are the subspaces. So we can visualize all these subspaces in R3. And I want to emphasize that the non-trivial subspaces in both R2 and R3, that is the lines for R2 and the lines and the planes for R3, for them to be a subspace, they must pass through the origin. Okay, so notice that key. So it's not any line can be a subspace. The line must go through the origin in R2 and R3. And for R3, not any plane is a subspace. Only if the plane goes through the origin. Good. So now we can make a sketch. Let me just do it up here, just to show you visually why if a line that doesn't go through the origin is not a subspace. Okay, it's not closed under addition, so vector addition. So here's 2 vectors, 2 points on that line. Okay, so they're pointing to positions on the line. So those 2 vectors, v1 and v2. Okay, those are 2 vectors in the line, but their sum, remember the way we add, so I'm going to use the yellow here. So we use the parallelogram law. So that is their sum, this one here. See, it's not on the line, v1 plus v2. Okay, so that will happen when the line doesn't go through the origin. The sum will not lie on the line. And similarly, you can see for scalar multiplication, if I multiply any one of these vectors by a scalar that's not 1, the vector won't lie on this line. Okay, but this case over here, if you do the same thing over here, add 2 vectors that are on that line, you'll get a vector on the line. If you take a vector on the line and multiply by a scalar, it will still be on the line. Okay, and I could do the same thing for planes, except the sketch will be a little bit more involved. Okay, so spanning sets. So this is also a notion that we learned in R2 and R3. So and linear independence and standard basis. So we'll just summarize that. So let me call this set W to be the span of a set of vectors in Rn. So V1 up to Vk. So I take k vectors. I denote the subset to begin with of vectors W to be the span of them. And remember, it's the set of all linear combinations. So I'm going to write it out here. So these, maybe I'll use the symbol C. That's customary in the book. C1, V1, C1, V1. These are all vectors, but you knew that. C2, V2, etc. up until the last one. Okay, such that the CIs are scalars. All right, so the span of a set of vectors is an infinite collection of vectors because I'm choosing all possible selections of scalars, even though I start with a finite set of vectors here, this finite set of vectors, I end up with an infinite set of vectors. Okay, but that's the span, as you knew, the set of all linear combinations. Now these ones, I'm going to make a note here because just from the definition of span, W is a subspace. Okay, so this is a nice way to assure yourself that your subset is a subspace if you take the span of a set of vectors. So it is a subspace. Okay, why? Well, it's closed under scalar vector addition and scalar multiplication. So it's closed, and this is a good exercise for you. Maybe we can talk about that during the lecture. Closed under addition and scalar multiplication. So I would suggest you guys do this one, this proof. Okay, it's a good exercise. And if you have any difficulty with it, we'll talk about it in the lecture. Okay, so this is what we're saying here is that the span of a set of vectors is automatically a subspace, but you should at least once just sit down and do this proof here. Why is it closed under addition? So take two vectors. Remember, I'm claiming it is a subspace, which means it is closed. So you have to do an abstract proof. You have to take two arbitrary vectors, add them up, and show that their sum is one of these vectors. And then you have to take an arbitrary vector and an arbitrary scalar and show that the scalar multiple, c times v, is also of this form. Okay, then you've proven that it's a subspace. But you can do that as an exercise. So that's spanning sets, and they happen to be subspaces, since we're talking about subspaces. Now, linear independence again. So let's start with that same a set of vectors again in Rn. Let's take k of them. Remember, k can be anything at the moment. Is linearly independent, and it's the same definition as before. We look at a certain independent if and only if C1 times V1. So look at a particular linear combination. Okay, that equals the zero vector if all Ci's are zero. Okay. Okay. So of course, this particular linear combination will be zero if the C's are all zero. So there's always one selection of C's which makes this linear combination zero. But if that's the only one, then it's linearly independent. Okay. It's linearly dependent then if there exists a set of scalars not all being zero. Okay, so at least one of the C's is non-zero, at least one, but whose sum is zero. Then it's linearly dependent. And we saw the consequences of that. So linearly independent, same definition. And then the standard basis in Rn, okay, so remember a basis. Well, we're going to define the basis just below here. So it's going to be a set of vectors denoted by E typically. Okay, so E1 to En, so a set of n vectors, and these E's are pretty special simple forms. So in components, E1 would have a 1 in the first component, but zeros everywhere else. Okay, and then E2, I'll just do a few here. So 0, 1 in the second component, and there. And in general, the EI vector, the ith vector, would be a vector that has a bunch of zeros, and then there's a 1 somewhere. Okay, so there's a 0. Let me redo that just to emphasize that there's nothing but zeros and ones in these vectors, and there's only a single one. Okay, so I'm going to put it there, and then I'll continue on with all zeros. So that's indicating that there's only one zero, and this is in the ith position, ith component. Okay, so pretty simple vectors. They have mostly zeros, n minus 1 zeros, and then just a 1 in that component that's specified by their subindex there. And therefore, En, let me just finish it off, will be this vector with lots of zeros all the way down until the last one. Okay, so there's your standard bases in Rn. Particularly simple vectors, and they're very nice for computations, as we will see. And notice too that Ei, while I'm here, the dot product of these vectors is 0 if I is not equal to j. Okay, so they're also orthogonal. All right, so finally, we're doing bases now. And this is the last topic. So bases of subspaces. So a basis is a set of vectors, first of all, that spans, so I should say here, set of vectors in subspace. So you start with a subspace, and you take a set of vectors from that subspace. And what's special about these sets of vectors? Well, they span the subspace, and the set of vectors is linearly independent. Okay, so I take a set of vectors that are linearly independent, and they span the subspace. Okay, so a simple example here is in Rn. So for Rn, the standard basis, I'll denote by script B. So I'm going to list a set of vectors, and they're going to be these standard vectors, basis vectors I specified above, is a basis for Rn. Okay, now we have to check those two things. Does it span Rn, and are they linearly independent? And it's clearly so. Spans, let me write it down here. So B spans now. How do you prove that a set of vectors spans Rn? Remember the span, let's go back up here. The span of a set, which is this W, so span of V1 to Vk, is the set of all linear combinations. So if you have a set of vectors, you're trying to establish that it's a basis for subspace, you have to show that the set of all linear combinations is that subspace. So the subspace we're talking about here is Rn. Does it span Rn? Well, that means you have to take an arbitrary vector in that subspace, which happens to be Rn, okay, and show that it can be written as a linear combination of the set of the vectors in that basis. So take a V in Rn, and I'll write it out component form. So V1 to Vn. The question is, can I write that as a linear combination of the EIs? And we see it's particularly easy because of the simple form of these EIs. So V can be written as the scalar V1 times the vector E1, the scalar V2 times the vector E2, and all the way down to the last component, Vn times En. Okay, so it spans Rn. That's the proof that this basis script B, the standard basis, it spans Rn. I took an arbitrary vector V in Rn, and I show that it can be written as a linear combination of the E's. That's an En here. Okay, and they're linearly independent is also an easy proof, is linearly independent. Independent. Okay, and that's easy one, because if you had C1 E1 plus all the way to Cn En equal the zero vector, remember the zero vector is this vector with n zeros in it, then just look at what this vector is. So C1 times E1 is C1, C2 times E2 is C2, gives me the C2 vector. If I just write out the components of this, all right, I get that vector, and this vector is supposed to be 0, 0, 0, all that, and therefore all the CIs must be 0. Okay, so it's linearly independent. Okay, that's a basis. I should point out that there's many bases. There are many bases for Rn. Okay, and that's part of the a very important aspect of linear algebra, both in theory and applications, is that we can select different bases for a subspace. There are many. Let me just write this down. Different bases. So this is the plural of bases for a subspace. I should say if subspace is not the trivial one. Subspace is not just the zero vector, because that's you find a basis for that subspace, it's just the zero vector. But if it's not that trivial subspace, then there's many different, actually infinitely many different bases for the subspace. So let me just give you some examples, and you can see for yourself. So there's some work to do when you want to prove that a set of vectors is a basis. Okay, so for example, let me just do an R2 here first. So 1, 1. So this is not the standard basis, is a basis for R2. Okay. So you have to prove two things, that this set of two vectors spans R2. So any vector can be written as a linear combination of these two. And you've seen examples like that in previous lectures, how to compute the components of this. And it's linearly independent. So it spans. So this is a topic for the office hour, is how to do this. So it spans R2 and is linearly independent. Notice you have to do both these things, and one doesn't imply the other. Okay, so both linearly independent. Only in special cases does one imply the other, okay? But you'll have to find that out later on. So that's an example of another basis in R2. So I think I'll stop here because this leads to other questions. Actually, I wanted to mention something up here when we were talking about the zero vector subspaces. Let me just squeeze it in here. It's a good thing since we're talking about the zero vector. Note every subspace. This is a useful fact to know. So every subspace contains the zero vector. Okay. So why this is useful? Because we often want to know whether a subset is a subspace. Yes or no answer. Either one. It's either yes or no, one or the other. This fact here, every subspace contains a zero vector, can be used to easily prove that a subset is not a subspace. So if you can tell that a subset doesn't contain the zero vector, then it's not at all a subspace. So that is corroborating what we saw above about lines or planes not through the origin. These are subsets of vectors that do not contain the zero vector. The zero vector is the origin, and therefore they cannot be subspaces. But how do you know this fact here? Every subspace contains a zero vector, because if you take a vector from that subspace, then Ku is in that subspace, right? So and I can take K to be any scalar, take K to be 0. Ku is the zero vector, okay? So because a subspace is closed under scalar multiplication, it must contain the zero vector, all right? So that's useful. If you can prove that a subset does not contain the zero vector, then you can establish that it's not a subspace. However, you can't use this to prove that a subset is a subspace, because many subsets of vectors contain the zero vector, but they're still not a subspace because they're not closed under addition or scalar multiplication. So it's only good for one particular aspect of this question. So I think I will stop here and see you next time for section 1.5.